Scientific notation word problems. The word problems are the fun ones, right? The table shown below gives the approximate distance from the sun to a few 5 different planets. How much farther, or further, I guess it's further, how much further in kilometers from the sun is Saturn than Venus? Okay, so these are all the different distances from the sun to those planets. And sometimes when we think how much farther, we think, oh, it's 3 times as far or 2 times as far. And that would be multiplication or division, but it's saying in kilometers. So it's not a number of times from farther, it's how far. Okay, so we're looking at Venus, and we're looking at Saturn, and we don't really care about the other ones. So Venus is 1.1 times 10 to the 8th, and Saturn is 1.4 times 10 to the 9th. And we can just subtract those as long as we have the same power of 10. So Saturn's farther, so I'm going to write that as 1.4 times 10 to the 9th, and Venus is 1.1 times 10 to the 8th. Well, one or the other we need to convert to so that they have the same exponent. So either we need to move this one one so that we have 10 to the 9th, which would be if we moved it to this way once, or we need this one to be 10 to the 8th, which would mean we moved this way once. So let's change this one times 10 to the 8th. So this would be times 10 to the 8th, this would be 14 times 10 to the 8th, right? Because we moved our decimal 1 to this way, and that subtracts 1 from there. So 14 times 10 to the 8th. Now we can just do 14 minus 1.1. And maybe add a 0 there, and we'll just do our subtraction. 10 minus 1 is 9, 3 minus 1 is 2, and 1 minus 0 is 12. So we have 12.9 times 10 to the 8th kilometers. That's great, and that is the answer, except that this isn't in scientific notation because this is a 12, and scientific notation has to be between 1 and 9. So we need this to be 1.29, and we can do that. 1.29 times 10 to the, if we move this way, then we're going to increase our exponent. So 1.29 times 10 to the 9th power. Okay, the average human heart beats 1.15 times 10 to the 5th times per day. That's a lot of heartbeats. There are 3.65 times 10 squared days in 1 year. That's 365, if you wanted to convert that. And actually, there's 3.6525 days in a year. Anyway, 1.15 times 10 to the 5th and 3.65 times 10 squared, and we need to multiply those because we want to know how many times it beats in a year. So this is per day, and there's days per year, so times per year, we multiply those together. And again, we need them to be in the same form for scientific notation. And then we can just multiply our numbers together. But we could also, actually, we're multiplying. I'm sorry, I was adding. We're multiplying. We don't need them to be in the same form for scientific notation. What we can do is just move all of our scientific notation numbers to the end. So we're going to have 1.15 times 3.65 times 10 to the 5th times 10 squared. So we're still multiplying all the same numbers together. We just move the order around, and that's fine. It's completely legal and legitimate, and doesn't change the answer at all. Okay, so 3.65, they didn't give us a calculator for this one, which I don't think was very nice, but that's okay. We can do the more fun way anyway. 5 times 5 is 25. 5 times 6 is 30, plus 2 is 32. 5 times 3 is 15, plus 3 is 18. And then we have 5, 6, 3, and 5, 6, 3. Add that all up. I have to put it over here because I ran out of space. And we have 5. 5 plus 2 is 7. 8 plus 6 plus 5 is 19. 3 plus 2 is 5. plus 6. 5 plus 6 is 11. And 4. So 41975. I have 4 decimal places, so I'm going to move 1, 2, 3, 4. And our heartbeat's 4.1975 times 10 to what? Well, if you remember your rules for exponents, you have 10 to the 5th times 10 to the 10 squared, same base, right? So we can write that as 10 to the 5 plus 2. Because if we were to write this out, it's 10 times 10 times 10 times 10 times 10, that's 5 times 10 times 10. And if we just list that out, it's 10 to the 7th, so 5 plus 2. So 4.1975 times 10 to the 7th times per year. So that's about 42 million times a year. So you need to find someone that will give you $1 for every time your heart beats in a year. And you'll be very well off by the end of the year. Except I did something wrong. Round to 1 decimal place. There we go. Each page of a top secret report on aliens requires 2 kilobytes of space in digital format. That is a well-known fact. What is the maximum number of pages the report can have so that it can be completely stored on a USB drive that holds 4.4 times 10 to the 6th kilobytes? Wow. That is an interesting problem. Okay, so each page is 2 kilobytes. And it holds 4 times 10 to the 6th. Wow. Let me start that over again. I'm sorry. Green for aliens. Okay, so 4 times 10 to the 6th kilobytes is our capacity, right? So that's 1,000 bytes. And each page takes 2 kilobytes. So 2 kilobytes per page. And so our answer is going to be in pages. And our kilobytes are actually going to disappear. Really, what we can do is we have 4 times, that's supposed to be a 10. Maybe I should be done for today. Sorry. Okay. So we have 4 times 10 to the 6th kilobytes, right? And this is multiplication and division. It doesn't matter what order we do this in. So we can just do our 4 divided by our 2, and that's going to give us 2. And then we can multiply by our 10 to the 6th. 2 times 10 to the 6th pages. And that's really all there is to that one. So 2 million pages. Which, I mean, that's a good summer read right there. Okay, the average human body cell is really small. 5.1 times 10 to the negative 4 centimeters. I mean, a centimeter is not all that big. And this is divided by 10,000. The diameter of a plant cell is 8, there's no point. I always want to have a point. 8 times 10 to the negative 3 centimeters. So also pretty small. What is the combined diameter of the body cell and plant cell? Okay, so on the Magic School Bus, you shrink down and you're comparing human body cells. And so you find this human body cell and you're like, oh, that's cool. And here's your diameter. It's 5.1 times 10 to the 4th. And you're like, well, let's compare that with a plant cell, which is bigger. And so you draw it. So I'm going to try this. You draw it. Now it looks really close to the same size. Anyway, you draw it right next to it. And then you're like, well, I wonder what the diameter of both of them together is. Because that's just something that I know we all lay awake at night wondering about. Okay, so this is 5.1 times 10 to the negative 4th centimeters. And this one is 8 times 10 to the negative 3 centimeters. And if we want to add those, we can do that, but we need to be in the same form, right? We need it to have the same power of 10. So if 8 times 10 to the negative 3, what would that be in 10 to the negative 4 with a 10 to the negative 4? Well, that would be 80 times 10 to the negative 4, because we would have to, if we make this an 80, in order to get it back to the same size, to move the decimal place enough times, we'd have to move to the left one more time. So that's why it becomes a negative 4. Okay, and then we're just going to add the 80 and the 5.1 times 10 to the negative 4. Okay, it's still going to be 10 to the negative 4, but that gives us 85.1 times 10 to the negative 4, which is great. But again, now we have the issue of this is not in scientific notation because it's, what's the word? Oh, it's not between 1 and 9. It needs to be between 1 and 9. And so we need to move our decimal this way once. And if we move our decimal that way once, we can take 1 off of that, so that's 8, because that's where we'd be moving anyway, right? We'd be moving to the left 4 times. If we move it to the left once, then we're only moving to the left 3 more times. So 8.51 times 10 to the negative 3rd. So now you know that if you take those two cells and put them next to each other, you know how long the diameters are together. All right, and that's it for this video.